So we talked about 6 different kinds of monolithics, as to speak. Now we got to the zirconium, which is really one of the most important issues that I will talk about in this series of lectures. That's called monolithic versus layered, because there is a big confusion about zirconia, the composition of zirconia, specifications of zirconia, indications of zirconia, physical properties, how to compare it with translucency, and all kind of issues. Even etching zirconia, printing zirconia, injecting zirconia. There's much to talk about when it comes to zirconia. Now this is a zirconium element in nature. This doesn't really concern us, the chemical part of it or anything. We're just going to talk about what concerns us as zirconium oxide here in dentistry. Now zirconium has been used, even in orthopedics as a replacement of the stainless steel knee joint or hip joint or shoulder joint or whatever. Like I said, we're going to discuss zirconia in these lectures as zirconium oxide, because this is the form that we use in dentistry. Now, the word monolithic here is a form, not to be confused with the word monoclinic here is a form, not to be confused with monolithic prosthesis. Monolithic means one layered, a monolayered. But monoclinic is a phase of zirconia that we will be talking about, the 3 phases of zirconia. Now those are the 3 phases of zirconia. We have monoclinic phase, we have tetragonal phase, and we have cubic phase. Now let's establish something here, that all we're talking about is zirconium oxide. It's the same composition. It's a zirconium oxide, all right? These are phases, the way the molecule looks like. The way the molecule of zirconia looks like, the way it's formed. This form of the zirconium molecules give you different physical properties. Some of them is very desirable, like tetragonal and cubic. Some of them is less desirable, like the monoclinic. So all you're talking about is zirconia. There isn't many kinds of zirconia. It's the one kind of zirconia that's called zirconium oxide that we use, but it has different forms, different molecule forms. And based on these different forms, we get different specifications and different physical properties of the zirconium, all right, of the zirconium oxide that we use in dentistry. Now, this phase, which is the monoclinic phase, exists to up to 1170 Celsius, all right? So from room temperature, from room temperature to 1170, all you have is monoclinic. Say that you heated this zirconia product here, it will deform from monoclinic phase to tetragonal phase. It will get a different shape, which is a tetragonal. In this phase, when you heat it up above 1170, let's say between 1170 to 2370, in this range of heat for zirconium, the molecules will look like tetragonal, all right, which is very desirable for us. And then if you heat it furthermore, then it will go from tetragonal phase to cubic phase, and that's between the temperatures 2370 and 2680. Okay, from 2370 to 2680, it will become, the molecule will reshape into a cubic phase. Now, of course, once it starts cooling down, it will go back from cubic phase to tetragonal phase, and then you keep cooling it down, it will go back from tetragonal phase to monoclinic phase, all right? So you heat it up, it changes. With these changes, there's a change of volume too. It decreases 5%, and it increases 3 to 4% in between monoclinic and tetragonal phase. So you heat it up, there's a volume increase of 3 to 4% from monoclinic to tetragonal. You cool it down, it goes back from tetragonal to monoclinic, losing 5% of volume, all right? Now this doesn't concern us because it's calculated by the CAD/CAM machine, and then it's all compensated for, and we don't have to worry about it. What we need to know is, since we like this phase, the tetragonal phase, and the cubic phase, we can't use it on high temperatures, of course. You want to use it on a room temperature, right? So once we heat the monoclinic and it becomes tetragonal, and we want this shape of tetragonal, we don't want it to go back to monoclinic when it cools down. So we have to use additives, right? We have to use stabilizers. And there's a Eutteum oxide stabilizer, and there's a aluminum oxide stabilizer. Now we're going to talk about these stabilizers. What they do is they prevent the tetragonal phase. Once it cools down, they prevent it from going back to monoclinic phase. So it is stabilized tetragonal zirconia. They stabilized this phase of the zirconia, the tetragonal phase. They stabilize it with Eutteum oxide. That's why you see the term Y3, for example, stabilized by 3 molecule weight of Eutteum. Tetragonal zirconia stabilized by 3 molecule weight of Eutteum, and we're going to talk about that in details. Same thing applies to cubic. You heat the tetragonal even more, it becomes cubic. You want it to stay at cubic phase, so you apply whatever stabilizers to keep it in the cubic phase after it cools down to the temperature of tetragonal or the temperature of monoclinic finally, because you're going to use something on room temperature. So pretty much it's about heating and stabilizing on a certain form, but at the end of the day it's zirconium oxide, ZrO2, all right, but different forms. Now we stabilize these forms, so when they go back to room temperature, we still have tetragonal phase and cubic phase. This is very important for us to understand, all right? So there is 3 phases of zirconia: monoclinic on room temperature up to 1170, tetragonal 1170 to 2370, and cubic 2370 to 2680, all right? And yes, we can stabilize them in that shape, which is cubic, or in the other shape, which is tetragonal, even though they're gonna cool down and come to room temperature. Still we can retain tetragonal and cubic phase with using stabilizers, all right? And we're going to talk about that in details, like we said. This is just for brainstorming. What is the maximum sintering temperature in your furnace? For us, we use a Mann-Gerbach milling machine from Germany, and the sintering furnace, it's a heat element sintering furnace, because we're going to talk about microwave sintering, and we're going to talk about different types of sintering. What I have is heat element sintering, and it's 1450. That's the maximum temperature of it. Now, this is a simple tetragonal shape. It's a cube that's stretched up. That's as simple as it can be described, all right? So A equals B, but doesn't equal C. A and B are the same, but C is stretched up. It's a stretched up cube, all right? That's the tetragonal form that we want. Now, up until 2014, only high-strength 3 Eutteum tetragonal zirconia, stabilized zirconia, was used for fabricating restorations, from single crowns to multi-unit implant-supported bridges. Of course, it was used as a core, and then we veneer or layer or stack. We build up on top of that core. All right. Now, this is a chart that became very popular. It's from Ivoclar Vivadent. It shows the generations of zirconia. What I want you to look at here, that up to 2014, we only had 3 Eutteum molecules tetragonal stabilized zirconia. All right, we're just gonna say 3Y for the easiness. 3Y tetragonal zirconia. All right, so 3Y tetragonal zirconia, 5Y tetragonal zirconia, 4Y tetragonal zirconia. We're just gonna say that. Now, up to 2014, what was the physical properties or mechanical properties? You look here, you find that translucency in general was low. There was a risk of low temperature degradation. We're going to talk about that, LTD, low temperature degradation. And mechanical properties were high. It was, strong material. Now, as we moved to beyond 2014, and 5 Eutteum stabilized zirconia came out in the market, in a form that we used here from Mangerbach, from the company that I use. I used these blocks. They were very translucent, but brittle. They broke like many times. It's unlike what we know about zirconia up to that 2014 year. After that, we had products that really translucent but weak. So mechanical properties were very weak, you know, and it had a low risk of LTD, but translucency, there's 4 pluses for translucency. It's the very translucent zirconia, very translucent zirconia. But they obtained this translucency by adding more weight percent of Eutteum, 5 Eutteum stabilized zirconia. And then we will see that there's other factors that you can play with to gain translucency. But up to this year, 2015, this is what they came up with. Translucency by increasing Eutteum regardless of mechanical property disadvantages. So we had a weak product, but a very high translucent product. And then they reduced this to in between, 4 Eutteum. Instead of 3 or 5, they got the 4 Eutteum stabilized zirconia. It's very popular until today, right? It's called HT Plus in the blocks that I use, or multi or high translucent or whatever. But I think that this 5 Eutteum is not an option anymore by itself, but it can be a continent of the zirconium block side by side with other continents. We will discuss that. But these days we have good mechanical properties, not very strong like the 3 Eutteum. Like if you want to go beyond 3-unit bridges, a 3-unit bridge, I would say we go back to a 3 Eutteum and then we stack or layer, but this is layered. If you really want to go with monolithic, you can use 4 Eutteum tetragonal zirconia. Translucency is acceptable, 3 pluses. Low risk of LTD, it's acceptable, 3 pluses. And then mechanical properties is 1 plus. It's not very strong, but I will show you what they exactly mean by that in this chart. All right. We're still talking about this block from Ivoclar Vivadent, which is Emax Zircad, like I indicated before. Zirconia block. Still, they call it Emax, but it's a Zirconia block. Emax Zircad, Zirconium block from Ivoclar Vivadent, when we're taking it as an example. Look, if you wanna, this is pretty much roughly the averages. Lithium disilicate, even from Ivoclar Vivadent, you're talking about 500 megapascal of strength. 3 Eutteum tetragonal stabilized around 1000, 4 Eutteum around 750, 5 Eutteum around 600, even plus and minus 50. So what does this mean? These 3 products are zirconium products, zirconium oxide, ZrO2, but with different content of stabilizer, which is in this case Eutteum stabilizer. There is aluminum oxide actually in it too, with a small percentage, or 1 or less, around 1%. We will see now. But anyways, 3 Eutteum, 4 Eutteum, 5 Eutteum, and lithium disilicates. Now, if we want to put these, if we want to dial in these into a table to see what's going on, this is the table. Look, here is the Emax Zircad low translucent or medium opacity, which is the high strength zirconium block. All right, it falls in the 1000 range, 1000 megapascal of strength. This is the 3 Eutteum. All right, now when we go down to 4 Eutteum of zirconia, you're talking about Zircad MT, medium translucency, or MT multi-layer. These, you're talking about Zircad MT here, medium translucent. When you get to medium translucent, it's more translucent, but it's weaker, so it falls into the 750. See, when you go back, it falls into the 750 range, 750 megapascal. All right, and then we talk about the 5 Eutteum stabilized zirconia, which is here, 600 tetragonal stabilized zirconia, and this falls around the 600 range. Now, if we look at the lithium disilicates, which is pressed, because the strongest is pressed, heat pressed, or heat injected, or pressed, it's stronger than the milled. And you want to compare the IPS Emax, which is lithium disilicate product, strength-wise, with The 5 Eutteum stabilized zirconia, which is the high translucent zirconia, you're talking about almost the same range. There is 100 megapascal of strength difference, initial strength, because there is aging for zirconia, and there is low temperature degradation, there's all kind of aspects that we will discuss, and there's benefits of cementation when it comes to lithium disilicate, and it gives strength, and then lithium disilicate do not have LTD, low temperature degradation. So there's differences. But initially, they're very close by. Talking about high translucent zirconia, it's close by lithium disilicate physical properties, and I want you to know that. I want you to know that because we're going to talk about products from different companies, you know, where the comparison when it comes to strength is pretty close between the high translucent zirconia and the lithium disilicate pressed ingots. Alright, so the strong zirconia is 3 Eutteum zirconia, 4 Eutteum zirconia, lower mechanical properties, acceptable translucency. Now let's look at this. This is also published by the scientific publication of Ivoclar Vivadent for their 3 Eutteum stabilized zirconia. Alright, let's look at it and try to understand something. Zirconium oxide, the content of zirconia in the zirconium block is 88 to 95% weight percent. Alright, so let's say 91% zirconia. Alright, Eutteum oxide, which is the stabilizer, remember we stabilized it with 3 molecules weight of Eutteum, so the weight is about, say, 5%. Hafnium oxide is a kind of impurity. It's I don't want to say it's hard to get rid of it, but it's expensive, and it takes much of manufacturing process, longer manufacturing process, which will cost money to get rid of this hafnium oxide. And companies figured out that a little bit of hafnium oxide impurities wouldn't change the physical properties of the zirconia that much. So that's the only reason why we have hafnium oxide. It's it's costly to get rid of the hafnium oxide. And then we have aluminum oxide, about 1 weight percent of aluminum oxide. We're going to discuss the effect of aluminum oxide on translucency and the effect of aluminum oxide on low temperature degradation. All right, so we're getting into more and more details, and it gets a little bit sometimes confusing, or you might lose your way there, but I'll try to make it simple. I'll try to keep it simple. Other oxides for coloring, let's say about 1%. So in other words, there is say that there is 90% of zirconium oxide. This zirconium oxide in the block, which is the 90% of the block, we want to know how much of this zirconium oxide, which is the 90% of the block, how much of this zirconium content in the block is tetragonal, how much is cubic, how much is monoclinic, and what makes the properties of the zirconia and the physical properties of the zirconia different from one block to another. Why there's a block that's 1200 megapascal of strength, another block that's 700 megapascal of strength, another block that's 557 like the katana, HTML and STMLs. STML is stronger, but HTML is weaker, but it's more translucent. So we're going to discuss what makes the difference here manufacturing wise, so you understand what's going on, why there's many blocks of zirconia in the market, why everyone tells you a different flux-core strength and a different translucency. How do they play with the continent? A little bit, like on a basic level, we're going to discuss that, not very deep, but at least you'll have a hunch, you'll have a sixth sense of if somebody advertised to you, oh, now we have cubic zirconia, oh, now we have high continent tetragonal zirconia. I want you, this is a try from me to help you elevate the knowledge that you have about the zirconium block, so you can at least say, oh, this doesn't make sense, or I need more information about this, or okay, you give me more translucency, but is it weaker now? Or okay, you're saying that it's strong and it's high translucent, But what's the LTD on this block? Low temperature degradation. Is it gonna am I gonna have a failure after 5 years? Is the LTD high or low? The risk of LTD on this block. So I want you to know about all of this. Low temperature degradation, aging of the zirconia. I want you to know about translucency, and I want you to know about strength and physical properties, etching and everything. And then I want you to compare what kind of composition makes this this difference. I know that this could be a little bit, you know, advanced and a little bit too much information, let's say, for a dental technician or for a dental practitioner, whether a dentist or a dental technician. But I find it imperative and essential for us to really, like I said, have a sixth sense, or have you know, when somebody advertises something to you, at least you know what they're talking about, and at least you can form a question that makes sense. So you would evaluate this new product. Is it really as strong as this salesperson is describing to me, or this advertising is illustrating, or is it less? Or how can I judge such a thing? Or at least how can I ask for more information and try to evaluate it? So pretty much we're gonna talk now about the zirconium oxide, the 90% content of zirconium oxide inside of the zirconia block. We're gonna see, is it tetragonal, is it cubic, is it a mix, does it have monoclinic in it, and what kind of specifications we might go through. All right, now first of all, this is just to show you that there's a core and there's a veneering ceramic. The core has its own megapascal of strength, and then the veneering ceramics has its own flexure strength. All right, so together it's very hard to give you a combined flexure strength of this prosthesis, because it depends on all kind of occlusal forces, lateral forces. Where is it applied? Is it applied here? Is it applied there? And many other factors of occlusion, many other factors of you know, I meant to say that even thickness is different from here to there. Occlusal forces are different from buccal to lingual to cervical, and then, you know, it's you can't really determine the strength of a layered prosthesis without looking at the occlusal forces, without looking at where does it fall in the patient mouth, and in which zone. Is it in the aesthetic zone? Is it in the functional zone? And things that we were going to be talking about. This is just for brainstorming at this part. Now we're going to talk about the amount and size of aluminum oxide, the effect of it on translucency, and we're going to put all the factors that affect translucency in one slide for easiness. But for now, I want you to know that aluminum oxide grains were minimized, leading to increased translucency. But it had another effect that we will talk about. I don't want to confuse you right now. But since you wanted more translucency, to increase the content of Eutteum oxide, resulting in two crystalline materials, which is 4 Eutteum and 5 Eutteum, and we're going to discuss the difference between both. Now, pretty much, the translucent material have smaller amount of tetragonal phase, 75% in 4 Eutteum and 50% in 5 Eutteum, leading to reduced possibility of tetragonal to monolithic transformation, which is toughening transformation. We were going to talk about that. It's a kind of crack propagation blocking mechanism as well. We will discuss that in details as well. But for now, I want to lead you to this to this illustration again. We looked at that. We said that these are the generations of the zirconia. But I want to show you that here in the 5 Eutteum molecules of tetragonal stabilized zirconia, 5 Eutteum stabilized zirconia, they reduced the amount of tetragonal to 50%. All right, and they increased the Eutteum content, and I would assume that they increased the cubic content as well. That's why it led into a weaker mechanical properties in 5 Eutteum zirconia is weak, but mechanical properties in 4 Eutteum zirconia is higher. It has a better mechanical properties because we increase the tetragonal continent. So in other words, the tetragonal continent is related to the strength. More tetragonal continent in the zirconium block, more strength and less translucency. Now, less tetragonal continent is less strength, and you can fill it up the other 50% with like cubic zirconia and to substitute for the Eutteum stabilizer, so it will be more translucent, but it's less mechanical property. At this point of the lecture, I just want to talk about tetragonal only by itself. More tetragonal phase zirconia in the zirconium continent of that block, a stronger product. Less tetragonal phase zirconia in the zirconia continent of that block, less strength, more strength. This is what I want to talk about strength in relation to tetragonal. More tetragonal stronger, less tetragonal weaker. All right, and then let's now move to the translucency factors. We talked about the strength factors. Now we're going to talk about translucency factors. As far as I studied and read throughout studies and throughout scientific papers, and this is all that I can collect from different sources, and I came up with this slide. Zirconia translucency factors, as far as I could gather, like I said, are 4. Aluminum oxide particle amount and size, inverse correlation. All right, if there's more aluminum oxide, then it's less translucent. If the particle size is bigger of the aluminum oxide, it's less translucent. All right, so we want less aluminum oxide for us to get more translucency, and it has a different effect that we will talk about later. All right, so aluminum oxide, it's an inverse correlation. Now when you talk about Eutteum oxide weight percentage, it's a positive correlation. The more Eutteum oxide inside of that continent of the zirconia, then it's more translucent. All right, then we talk about amount of tetragonal zirconia phase particles, inverse correlation. The more tetragonal, yes, it is stronger, but it is less translucency. In this slide, we're talking about translucency. So more tetragonal, less translucency. While more cubic zirconia phase will give you positive correlation, will give you more translucency. So there is 2 things, which is cubic zirconia and Eutteum oxide, that will increase the translucency of the zirconium block, and there's 2 things that will decrease the amount of translucency, which is addition of aluminum oxide, which is the size and the amount. Both size and amount of aluminum oxide will decrease translucency, and the amount of tetragonal zirconia, the more tetragonal zirconia, it will decrease the translucency. So those are the 4 factors. All right, now for example, look at this. This company is a German company, DD Dental Direct. They manufacture zirconium blocks. They call it high strength cubic zirconia system. They illustrated that they have 30% cubic crystals and 70% tetragonal crystals, and they have a very strong zirconia. Now we're going to discuss this in details, but let's proceed with our zirconia specifications. Now full contour crowns and full contour 3-unit bridges with higher wall thickness is recommended. All right, we're going to talk about wall thickness. We're going to talk about preparation guidelines in details. We're going to bring spear education examples about both lithium disilicate monolithic and zirconia monolithic and the reduction desired for it, and then we're going to talk about some companies' publications about reduction and preparation guidelines. All right, so here we hit the half an hour that we talked about. Let's delay LTD, which is low temperature degradation, to the next video. In the next video, we're going to discuss aging of the zirconia. Thank you for watching. See you in the next video.